Welcome back. In this video, we're going to study the graphs of quadratic functions in standard form. The graph of a quadratic function is a parabola, and we see these in real life in things like the cross-section of car headlights or on satellite dishes, whether they're those huge satellite dishes that you might see on the top buildings, or even the satellite dish at your home to get your cable or your satellite TV. The graph of our base parabola is taken from the equation y equals ax squared, or in function notation, f of x equals ax squared, where a is equal to 1. And I call the base parabola Joe parabola, kind of in deference to the average Joe. This is our standard typical parabola. So a will always be 1. The coefficient on our quadratic term is 1. The vertex of our parabola will be at the origin. It's considered to have standard width because of the coefficient is 1. And it will open upward. So Joe parabola will look something like this. Our typical width, if we input 1, we will output 1. If we input 1, we will output, or if we input negative 1, we'll output 1. If we input 2, we'll output 4. And if we input negative 2, we'll output 4. You can see here our graph will be the same on the right as it is on the left of this line of symmetry. And in Joe parabola, our line of symmetry is just the y-axis. So there's Joe parabola. If we input 3, we would output 9. If we input negative 3, we'd output 9, and so on and so forth. As we have seen, standard form of a quadratic is ax squared plus bx plus c, where a is the coefficient on our quadratic term, b is the coefficient on our linear term, and c is our constant. So to give you a summary of standard form and what happens, if a is greater than 1, or if a is positive, our parabola, whether it's Joe or not, will always open upward. If a is negative, our parabola will open downward. So now if a, or the absolute value of a, is greater than 1, okay, so if our quadratic is greater, the absolute value is greater than 1. So even if it's a fraction, I don't like to say it's a fraction, it could be like 3 halves, a could be 4, a could be 12 sevenths. Okay, these are all greater than 1. Our parabola is going to be narrower because of this multiplier. It's actually going to rise much faster for every input. It's going to be a lot steeper than Joe is. Okay, so this might be 1. This might be negative 1. So it might rise quite a bit faster. Whereas if the absolute value of a is less than 1, we'll have a wider parabola. Okay, it means it's going to go up quite a bit slower. So it might be fatter and much more flat. Okay, so if we have things like a 1/3 for a, 1/3 x squared, or 1/2 x squared, or any of those types of numbers. Anything less than 1, even like 8/9 x squared. Okay, a is 8/9, a is 1/2. Even 8/9 is going to be just a little bit flatter than Joe parabola. And one nice thing about standard form is the y-intercept is always our constant. Remember, the y-intercept, we set x equal to 0. Well, if you look at standard form, you put 0 in for x, then we have 0x squared and 0x, So what happens when we put 0x, or 0 for x, our constant becomes our output, so our y-intercept will always be c. One of the highlights of this video is learning how to graph a quadratic with only 5 points. And it's 5 key points, and we can get a really good idea of what our parabola looks like in as few as 5 points. So if we have standard form, so let's say we have like f of x equals x squared minus 2x minus 8. And we want to graph our parabola. Okay. Well, the y-intercept is easy, right? Didn't we say the y-intercept is c? Right? We set x equal to 0 and solve for y, so our y-intercept is down here at negative 8. That's our y-intercept of our parabola. So that's the first thing we can find. The second thing we can try and find are the x-intercepts. If we have real x-intercepts, that'll be very helpful. If we have imaginary ones, well, then we have some other things we need to do. But find the x-intercepts, or the zeros, or the roots of the solutions. Well, there are 4 ways to determine the x-intercepts depending on what you're given in standard form. Certainly, if you can factor, you want to be able to factor that. If b is equal to 0, if you have no linear term, well, then you can square root both sides and find your x-intercepts. You could complete the square, and of course you can always use as a last resort the quadratic formula. So let's go ahead. I think this is factorable, so we set f of x or y equal to 0, right? Because or y is 0 along the x-axis, we're finding those x-intercepts. And I think this factors to x minus 4 times x plus 2. So x equals 4 and x equals negative 2. Those are our x-intercepts at negative 2 and 1, 2, 3, 4. Then we want to find the axis of symmetry. Okay? We want to see where our parabola is reflected about. So we can always find the axis of symmetry by taking the opposite of b over 2a. So the opposite of b here would be the opposite of negative 2 all over 2 times 1. That's 2 over 2, and that's 1. So our axis of symmetry is here at x equals 1. And you may notice 1 evenly splits our 2 x-intercepts. Well, that totally makes sense. A parabola is symmetrical about the x-axis, or about its axis, about the axis of symmetry. So it totally makes sense that this would split evenly wherever our 2 x-intercepts are. Those would be the same distance to the right and to the left of the axis of symmetry. So we could have eyeballed this from the x-intercept in this case. We can see that this is 3 units to the right and 3 units to the left of our axis of symmetry. And since the axis of symmetry passes through the vertex, this value is also the x-coordinate of the vertex. So we already know now part of our vertex. Okay? So then that's the next thing we want to find out. We want to find out our vertex. We want to find out the top or the bottom of our parabola. Well, we should know from our original function here that since a is equal to 1, our parabola is going to open upwards. So let's find the vertex. We know that the x-coordinate of our vertex is 1, because that is on the vertex will fall on the axis of symmetry. So all we need is the y-coordinate. So in my function, I'll substitute f of 1, and I get 1 squared minus 2 times 1 minus 8. So I get 1 minus 2 minus 8. So my output, when I input 1, I output negative 9. So my vertex is at 1, negative 9. So it's going to be right there is going to be my vertex. So I am just about finished graphing my parabola. I just need one more point. Right? I said I would do this in 5 points. We have 1, 2, 3, we have 4 points. We need to do one more, and that's the point symmetrical to the y-intercept. Since all points are reflected across the axis of symmetry, we can take the reflection point of the y-intercept. So our y-intercept is here. We're 1 unit away, so we only need to go 1 more unit to the right, still at negative 8, and that point is at 2, negative 8. So that is our point symmetrical. So we can graph our parabola to the right of our axis of symmetry and to the left of our axis of symmetry, and there you go. So let's do another sample. F of x equals x squared minus 6x plus 5. Hopefully you know that the y-intercept, you can eyeball that, is at 0, 5. So 1, 2, 3, 4, 5. Find the x-intercepts. Well, let's see if we can factor. That looks like that might be factorable. See if we can factor that. I'm making a note here that my parabola opens up also because a is positive, so my parabola is going to open up. Can we factor that? 0 equals, would that be x minus 5 times x minus 1? And it would. Using our zero product property, I get x equals 5 and x equals 1. So 1, 2, 3, 4, 5. Now, we might be able to eyeball our axis of symmetry because we know that's going to split the x-intercepts in 2. So it looks like we're going to split it in 2 right here. So 1, 2, 3. So our axis of symmetry is x equals 3. We can check that with the opposite of b over 2a, which is the opposite of negative 6 over 2 times 1. 6 over 2 is 3. Look at that, confirmation of that. And then finally our vertex is going to be at 3 and then something, right? Because we know our vertex is going to lie on the axis of symmetry. So all I have to do is put 3 into my function and see what I get for an output. And so f of 3 equals 3 squared minus 6 times 3 plus 5. So it's 9 minus 18 plus 5, negative 4. So 3, negative 4, 3 on the x. So my vertex is down here at 3, negative 4. And the final point that I need is my point symmetrical. So I am 3 units away here. So I'll go 3 more units. And that particular point is now located at 6, 5. And I can go ahead and graph my parabola. This final sample, I will leave this one for you to do, but I'll get you started on this. We have a negative x squared, so I know this parabola is going to open down. The y-intercept is at 0, 5. The x-intercepts This does not look like it's going to be factorable, so I would recommend you use the quadratic formula, and then your axis of symmetry and your vertex and your point symmetrical to the y-intercept. So see if you can find those particular points and create the graph of that parabola, and I will see you in class.